High in the Peruvian Andes, at an altitude where the air grows thin and modern machinery struggles to function, stand structures that defy logical explanation. Massive stone blocks, some weighing more than 100 tons, fit together with such precision that a razor blade cannot slide between them. No mortar holds them in place. No wheels transported them. No written records explain how they arrived. These are the remnants of the Inca Empire, and their construction represents one of history's most profound engineering mysteries. The civilization that built Machu Picchu, Sacsayhuaman, and dozens of other architectural marvels accomplished what seems impossible by modern standards. They moved mountain-sized stones across treacherous terrain, lifted them to dizzying heights, and assembled them into structures that have survived 5 centuries of earthquakes in one of the most seismically active regions on Earth. Yet the Inca possessed no knowledge of the wheel for transportation, no iron tools, no draft animals capable of hauling such weights, and no written language to preserve their methods. What they did have was an understanding of physics, geology, and human organization that modern engineers are only beginning to appreciate. The story of how the Inca moved these colossal stones begins not with the stones themselves, but with the empire that demanded their movement. In 1532, when Spanish conquistador Francisco Pizarro first encountered the Inca Empire, he found a civilization controlling nearly 3,000 miles of South American territory. From modern-day Colombia to central Chile, the Inca had unified dozens of distinct cultures under a single administrative system. At its peak, the empire governed between 10 and 12 million people, making it the largest state in the pre-Columbian Americas. The capital city of Cusco sat at the empire's heart, a metropolis of 40,000 inhabitants where temples gleamed with gold and agricultural terraces climbed mountainsides in geometric perfection. The Inca called their realm Tawantinsuyu, meaning the 4 regions together, and they connected these regions with a road network spanning 25,000 miles. Along these roads, relay runners called chasqui could carry messages from Cusco to the empire's furthest reaches in less than a week, covering distances that would take modern vehicles days to traverse. But the most impressive achievement of Inca civilization was not organizational. It was architectural. The fortress complex of Sacsayhuaman overlooks Cusco from a hillside position that offers commanding views of the sacred valley below. Its 3 massive terraced walls stretch across 400 meters, constructed from limestone blocks that weigh between 90 and 200 tons each. The largest known block, situated in the foundation, measures approximately 9 meters tall, 5 meters wide, and 4 meters thick. Calculating its volume using limestone's density yields a weight estimate of 360 tons, equivalent to nearly 500 full-grown horses or 3 Boeing 747 aircraft. This single stone somehow traveled from a quarry located 3 miles away, ascending slopes that angle at 25 degrees in some sections. No traces of roads or ramps survive between the quarry and the construction site. Archaeological surveys of the terrain reveal no evidence of the infrastructure that modern engineering would consider essential for such a task. The stone simply arrived, was lifted into position, and was fitted so perfectly against its neighbors that 500 years of weather have failed to shift it even a millimeter. Traditional explanations for Inca stone-moving techniques have revolved around brute force. Early Spanish chroniclers, witnessing the tail end of Inca construction projects, reported seeing teams of workers dragging stones using rope made from plant fibers. Pedro Chiesa de Leon, writing in 1553, described 20,000 men pulling a single great stone, with thousands more waiting to relieve them when exhaustion set in. These accounts led historians to conclude that the Inca simply overwhelmed engineering challenges with massive labor forces. The theory held that tens of thousands of workers, organized through the Mita system of mandatory public service, could accomplish through collective effort what machinery accomplishes today. Mathematical models based on this assumption suggested that a 100-ton stone might require 8,000 workers pulling in coordinated rhythm, guided by foremen who called out commands to synchronize the effort. For generations, this explanation satisfied academic curiosity. Then engineers began running the numbers. A team from the University of British Columbia conducted a detailed analysis in 2019, examining the friction coefficients of limestone against various surfaces and calculating the force required to overcome static inertia for blocks in the 100-ton range. Their findings revealed a fundamental problem with the brute force hypothesis. On level ground, moving a 100-ton stone would require approximately 2 million newtons of force just to overcome initial friction, even assuming ideal conditions and perfectly smooth surfaces. Translating this into human effort, with each worker capable of sustained pulling force of roughly 300 newtons, yields a minimum requirement of 6,700 workers. This number assumes perfect efficiency, with every worker's force transmitted directly to the stone, with zero loss to rope stretch, friction between rope and stone, or coordination failures. In reality, efficiency losses in pre-industrial hauling systems typically exceed 50%. The actual workforce needed would likely double, requiring more than 13,000 people pulling simultaneously. Now consider the logistical impossibility of positioning 13,000 people around a single stone with rope access. Consider the coordination required to make them pull in perfect unison. Consider the terrain they would need to traverse, where narrow mountain paths barely accommodate a dozen people walking single file. The mathematics suggest that brute force alone cannot explain what the Inca accomplished. Something else was at work, something more sophisticated than simply throwing human labor at an impossible problem. The quarries tell a different story than the one written in colonial chronicles. At Rumicolca, 15 miles southeast of Cusco, volcanic andesite was extracted from mountainside deposits using techniques that left visible traces in the rock face. Archaeologists examining the site in 2007 discovered a pattern of small holes drilled in precise linear arrangements along natural fracture lines in the stone. Each hole measures approximately 3 centimeters in diameter and 15 centimeters deep, spaced at regular intervals of 20 to 30 centimeters. The pattern suggests a sophisticated understanding of geology that goes far beyond random hammering. The Inca identified weakness planes in the rock structure, zones where the molecular bonds between crystals were naturally less stable. By drilling holes along these planes and inserting wooden wedges, they created controlled fracture points. When water was poured over the wedges, the wood expanded with tremendous force. In the cold Andean nights, that water froze, expanding further. The cumulative pressure from dozens of expanding wedges could crack a 100-ton block free from the mountain with minimal effort and remarkable precision. Modern granite quarries use essentially the same principle, substituting steel wedges and hydraulic pressure for wood and ice. But the fundamental physics remains unchanged. Once freed from the quarry, the stone blocks presented a new challenge that has puzzled researchers for decades. How does a civilization without wheeled vehicles transport objects weighing more than the largest modern trucks across mountain terrain that modern roads struggle to navigate? In 2003, a French architect named Jean-Pierre Protzen conducted a series of experiments at the original Inca quarry sites, attempting to recreate their stone-moving methods using only technologies available in the 15th century. His team constructed wooden sledges based on designs found in fragmentary Inca artwork and tied them to a 15-ton limestone block using ropes made from agave fibers, matching the materials described in Spanish colonial accounts. 40 workers attempted to pull the sledge across level ground. The results were discouraging. Even with the ground wetted to reduce friction, the sledge barely moved. The workers exhausted themselves after moving the stone less than 50 meters in 4 hours. Scaling up this effort to move 100-ton blocks across miles of terrain seemed physically impossible. Protzen realized that the conventional model was missing a critical element. The breakthrough came from examining Inca roads with fresh perspective. Unlike Roman roads, which were built as straight as possible to facilitate military movement, Inca roads follow seemingly irrational paths. They zigzag up mountainsides in elaborate switchbacks, sometimes doubling the distance between 2 points when a more direct route appears available. For years, archaeologists attributed this to religious or ceremonial purposes, assuming the Inca chose scenic or spiritually significant routes over practical ones. But a civil engineer named Vince Lee, studying the road networks in the 1980s, recognized something the archaeologists had missed. The switchbacks maintained nearly constant gradients of between 5 and 7 degrees, even when steeper or flatter sections would have been easier to construct. This consistency suggested engineering priorities, not spiritual ones. A constant, gentle slope offers tremendous mechanical advantages when moving heavy objects. On a 7-degree incline, gravity assists the work. A stone being pulled upward can be secured with simple wooden chocks during rest periods, preventing it from sliding backward. The reduced angle means less force is required to overcome gravity's downward pull. Most importantly, the path can be reversed on the descent, allowing gravity to assist rather than resist the movement. The Inca weren't choosing the longest route. They were choosing the route that required the least force. Further examination of the road surfaces revealed another sophisticated adaptation. At regular intervals along known stone transport routes, archaeologists discovered sections where the road surface composition changed dramatically. Instead of the packed earth and gravel typical of Inca roads, these sections were paved with rounded river stones of remarkably uniform size, each approximately 10 to 15 centimeters in diameter. When Protzen's team recreated these surfaces and attempted to pull their 15-ton test block across them, the difference was extraordinary. The rounded stones acted as primitive ball bearings, rolling beneath the sledge and reducing friction by an estimated 60%. The same 40 workers who had struggled to move the block 50 meters on flat ground could now pull it up a gentle incline with relative ease. The technique required careful maintenance. Workers would need to constantly monitor the stone surface, replacing any river stones that cracked under pressure and ensuring the pathway remained level. But the labor required for maintenance was trivial compared to the labor saved in transport. A 100-ton block that might have required 13,000 workers on a conventional surface could potentially be moved by fewer than 5,000 on a prepared rolling stone roadway, assuming the gradient remained constant and gentle. Yet even this revelation doesn't fully explain the most impressive aspect of Inca stone transport. The largest blocks at Sacsayhuaman didn't just travel across gentle slopes on well-prepared roads. They traveled across rivers, through narrow valleys, and up final approaches where no amount of gradient management could reduce the angle below 15 or 20 degrees. At these critical junctures, the Inca needed a different technology entirely, one that could multiply human force by factors of 10 or 20. Evidence for this technology comes not from Peru, but from experimental archaeology conducted in the 1990s by a team led by researcher Gordon McEwen. His group examined pre-Columbian fiber ropes preserved in desert conditions along Peru's coast, analyzing their construction techniques under electron microscopy. The ropes were not simple, twisted fibers, as Spanish accounts had suggested. They were complex braided structures, incorporating up to 600 individual agave strands, woven in patterns that distributed tension evenly across the entire cross-section. Tensile strength tests on reconstructed rope samples revealed breaking points exceeding 40,000 newtons per square centimeter, comparable to modern steel cable of equivalent diameter. More importantly, the ropes showed evidence of being used in pulley systems. Wear patterns on ancient rope fragments indicated repeated passage around cylindrical objects under high tension, creating distinctive flattening and fiber alignment that only occurs when rope moves around a fixed curve while bearing heavy loads. The Inca had no metal pulleys, but they didn't need them. Smooth wooden rollers, potentially lubricated with animal fat or plant oils, could serve the same function. Archaeological excavations at construction sites have uncovered post holes arranged in geometric patterns that make no sense as building foundations, but align perfectly with the anchor points needed for mechanical advantage systems. By threading rope through multiple pulley points, the Inca could achieve force multiplication ratios of 6 to 1 or higher. A team of 2,000 workers, instead of generating 2,000 units of pulling force, could generate 12,000 units when working through a properly designed pulley array. Suddenly, the impossible becomes merely difficult. A 100-ton stone requiring 12,000 units of force could be lifted, shifted, or pulled up steep inclines by a workforce small enough to actually fit in the available space around the stone. The precision of Inca stonework represents a challenge that transcends mere transportation. At the temple complex of Coricancha in Cusco, stone blocks fit together with tolerances measured in fractions of a millimeter. Individual stones feature 12 or more precisely angled faces, each cut to interlock with its neighbors in three-dimensional geometric complexity that rivals modern computer-aided design. No two blocks share identical dimensions, yet every surface matches perfectly with the surfaces surrounding it. The craftsmanship appears supernatural until one examines the tools left behind in abandoned quarries and construction sites. Scattered across these locations, archaeologists have recovered thousands of river-smooth stones, ranging from fist-sized to football-sized, each showing distinctive wear patterns on specific surfaces. These are hammer stones, and their distribution reveals the Inca approach to shaping rock. Rather than cutting stone with harder materials, as Egyptian or Roman masons did with copper and iron tools, the Inca used percussion. They struck softer hammer stones against harder building stones in a process called pecking, gradually pulverizing the surface layer and removing material grain by grain. In 1986, engineer Jean-Pierre Protzen conducted time-motion studies to determine how long this process would require. Working with locally quarried andesite and using river stones as tools, he attempted to create a flat surface on a block measuring 1 meter square. After 8 hours of continuous pecking, striking the stone surface approximately 60 times per minute, he had removed a layer roughly 5 millimeters deep across the entire face. The surface wasn't perfectly flat, varying by about 3 millimeters across its breadth, but it demonstrated that the technique was viable. Scaling up this experiment to a typical Sacsayhuaman block with 6 finished faces, each measuring approximately 2 square meters, suggested a time investment of roughly 900 work hours per stone just for surface preparation. The largest blocks, with their 12 or more angled faces and greater surface area, would require 3,000 hours or more. This calculation assumes skilled workers maintaining consistent rhythm and achieving efficiency similar to Protzen's experimental efforts. In reality, training workers to the necessary skill level would take months, and fatigue would reduce productivity. A single massive stone might represent 10,000 hours of pecking work, equivalent to 5 workers laboring full-time for an entire year on that stone alone. The mathematical implications are staggering when applied across entire construction projects. Sacsayhuaman contains approximately 70,000 cubic meters of precisely fitted stone. If we conservatively estimate that 25% of each block's volume required surface finishing through pecking, and that skilled workers could process 1 cubic meter of stone per 1,000 hours, the total labor investment for stone finishing alone exceeds 17 million work hours. Distributed across a theoretical workforce of 10,000 laborers working year-round, the project would require nearly 200 years. Yet archaeological evidence and Spanish chronicles both suggest Sacsayhuaman was constructed over a period of approximately 60 years during the reigns of 3 Inca emperors. The timeline only works if the labor force numbered in the tens of thousands, and if the organization of that labor achieved efficiency levels rarely seen in pre-industrial societies. This is where the Mita system becomes crucial to understanding Inca engineering achievements. The Mita required every able-bodied person in the empire to contribute a certain number of days each year to state projects. During those days, the state provided food, housing, and tools. Workers arrived in rotating shifts, ensuring continuous progress while preventing the exhaustion that would occur if the same individuals worked year-round. Colonial records preserved by Spanish administrators who adopted modified versions of the Mita system describe organizational hierarchies that managed these rotating labor forces with remarkable sophistication. Groups of 10 workers reported to a foreman, 10 foremen reported to a supervisor, 10 supervisors reported to a manager, and so on, creating a pyramidal command structure that could coordinate the efforts of tens of thousands while maintaining accountability at every level. Workers specialized in specific tasks based on aptitude and training. Some became expert stone peckers, developing the rhythm and strength needed for efficient material removal. Others specialized in rope work, learning to braid the complex fiber structures and operate pulley systems. Still others managed logistics, ensuring continuous supplies of food, water, tools, and replacement workers. The system resembled a massive, well-oiled machine, with each component performing its designated function in service of the larger objective. But human organization alone cannot explain the precision of Inca stonework. The tolerances achieved at sites like Quarrying require measurement and adjustment techniques that match or exceed pre-industrial European capabilities. Analysis of finished Inca stonework reveals a consistent approach to achieving perfect fit between irregular blocks. Each stone shows evidence of multiple fitting attempts, with small areas of concentrated pecking indicating where high spots were gradually removed. The process appears to have been iterative. Workers would place a stone in approximate position, mark the contact points where it touched neighboring stones, remove it, peck down the marked high spots, then repeat the process. After dozens of iterations, the stone would settle into perfect contact across its entire perimeter. Modern stonemasons attempting to recreate this technique using traditional tools have confirmed its viability, but expressed amazement at the patience required. A single 12-faced block might need to be lifted, positioned, marked, removed, and adjusted 50 or more times before achieving final fit. Each cycle requires the coordinated effort of dozens of workers operating ropes and levers to move the multi-ton mass. The physical demands are extreme, but the technique works without requiring any tools or knowledge beyond what the Inca possessed. The question of measurement precision leads to another technological mystery. How did Inca masons ensure that angles remained consistent across multiple surfaces when they had no metal squares, no levels, and no plumb lines of the type used in European construction? Evidence from tool caches discovered at construction sites provides intriguing answers. Archaeologists have recovered wooden implements shaped like large compass dividers, with two arms joined by a wooden pin that allows the angle between them to be adjusted and locked in place. These tools could transfer angles from one stone to another, ensuring consistency even when working with irregular shapes. Water levels, created by partially filling a stone channel with water and observing where the liquid surface settled, provided perfectly horizontal reference planes. Weighted cords, hanging under gravity's influence, established true vertical lines. Combined with the practice of working from carefully prepared foundation stones, whose surfaces had been pecked to perfect flatness over months of patient labor, these simple tools enabled precision that appears impossible without modern instruments. The Inca approach to construction was fundamentally different from European methods, where European masons cut standardized blocks and assembled them like bricks, using mortar to compensate for imperfect fit. The Inca treated each stone as a unique puzzle piece. They created interlocking three-dimensional jigsaws where every element supported every other element through friction and precise contact. The result was structures that could flex and shift during earthquakes without collapsing, as the stones moved slightly, then resettled into their fitted positions once the shaking stopped. The engineering achievements that enabled the Inca to move 100-ton stones and construct earthquake-proof architecture were not isolated technical accomplishments. They were expressions of a broader worldview that understood landscape, labor, and permanence in ways fundamentally different from European thinking. When Spanish conquistadors first encountered Inca cities, they saw primitive societies lacking the basic technologies of civilization. No wheels, no written language, no iron tools, no domestic animals capable of heavy labor. What they failed to recognize was that the Inca had deliberately chosen alternative technological pathways that were, in many ways, superior to European approaches for the specific challenges of Andean geography. The wheel, so central to European transportation and machinery, offers minimal advantage on steep mountain slopes where friction and gravity make wheeled vehicles impractical. Written language, the foundation of European record-keeping, was unnecessary for a society that developed quipu, a sophisticated system of knotted cords that could encode numerical data, calendar information, and potentially even narrative content. Iron tools, prized in Europe for their durability, were less useful than the Incas' bronze and stone implements in an environment where ore deposits were scattered and the fuel needed for smelting was scarce. The Inca looked at the resources and constraints of their environment and developed technologies optimized for those specific conditions. This philosophy extended to their approach to stone construction. In regions prone to seismic activity, where earthquakes could topple mortared walls and rigid structures, the Inca built flexibility into their architecture. The precisely fitted stones at Sacsayhuaman and other sites were designed to move during tremors, shifting slightly on their bases before settling back into position when the shaking stopped. Spanish colonial buildings constructed on top of Inca foundations tell a revealing story. During the devastating earthquake that struck Cusco in 1650, every Spanish structure in the city collapsed or suffered catastrophic damage. The Inca walls beneath them, including sections built 5 centuries earlier, remained standing without a single stone displaced. The same pattern repeated in 1950, when another major earthquake reduced colonial-era churches and government buildings to rubble, while Inca foundations stood undamaged. Modern seismologists studying these structures have confirmed that the trapezoidal shape of Inca doorways and windows, the inward lean of their walls, and the interlocking design of their stonework all contribute to seismic stability. The Inca were building to last not just decades or centuries, but millennia, and they succeeded in ways that modern engineering is only beginning to appreciate. The organizational systems that made Inca construction possible also reveal sophisticated understanding of human psychology and social dynamics. The Mita labor system, which might appear to modern eyes as a form of forced labor or slavery, functioned quite differently in practice. Workers fulfilled their obligations for a set period, often during agricultural off-seasons, when farm work was minimal. In exchange, they received food, housing, and the social prestige that came from contributing to state projects. Communities competed for the honor of providing workers for the most important constructions, viewing their participation as a source of collective pride. The system created a sense of shared ownership in imperial projects that would have been impossible to achieve through paid labor or slavery. When workers returned to their home villages after completing their Mita service, they carried with them stories of the great works they had helped build, reinforcing social cohesion and loyalty to the empire. The roads they constructed facilitated trade that enriched their communities. The terraces they carved into mountainsides increased agricultural productivity that fed their families. The temples and fortresses they erected stood as visible symbols of their civilization's power and permanence. This psychological investment in collective achievement may be the Incas' most sophisticated technology, one that modern societies struggle to replicate. Archaeological research conducted over the past 3 decades has gradually assembled a comprehensive picture of Inca stone-moving techniques, but significant mysteries remain. At Ollantaytambo, a fortress complex in the Sacred Valley, 6 enormous rose-colored granite blocks stand in a row, each weighing approximately 50 tons. These monoliths originated in a quarry located across the Urubamba River and 5 kilometers away on the opposite mountainside. Transporting them required crossing a river gorge hundreds of meters deep, ascending slopes that approach 40 degrees in places, and somehow raising the stones to a construction site perched on a mountain platform. No trace of ramps, roads, or infrastructure survives that could explain how the Inca accomplished this feat. Researchers have proposed theories involving spiral ramps that were dismantled after construction, or terraced approaches that were later buried or eroded away. Some suggest the Inca might have used the river itself, floating stones across on rafts during seasonal periods when water levels were high enough to reduce the effective weight. Each theory has supporting evidence and logical problems. The truth may involve a combination of techniques adapted to specific local conditions that varied from site to site based on available resources and terrain challenges. What remains indisputable is that the Inca moved these stones and constructed structures that endure 5 centuries after the empire's collapse. They did so without technologies that modern engineering considers essential, proving that innovation takes many forms and follows many paths. The great mistake of the Spanish conquistadors was assuming that technological sophistication could be measured by the presence or absence of specific tools. A civilization without wheels or written language appears primitive only if one believes those technologies are universally necessary. The Inca demonstrate that alternative approaches, developed in response to specific environmental and social conditions, can achieve results that equal or surpass conventional methods. Their legacy persists not just in the stones they moved and the buildings they constructed, but in the questions they force us to ask about the nature of progress and achievement. Modern engineers visiting Inca sites often experience a humbling recognition that their advanced tools and knowledge might not enable them to replicate these ancient accomplishments. A construction project using 21st century technology might move a 100-ton stone more quickly than Inca methods could, but it would require millions of dollars in equipment, fuel, and specialized expertise. The Inca accomplished the same result with rope, wood, river stones, and human labor. The final lesson of Inca engineering may be the most important one. They built an empire that, At its peak was the largest state in the Americas, controlling a population of 12 million across diverse ecological zones from coastal deserts to high-altitude plateaus. They achieved this without conquering through technological superiority in weapons or transportation. Instead, they offered administrative efficiency, agricultural innovation, and architectural permanence. Communities that joined the empire gained access to the road network, participated in the labor system that built terraces and irrigation systems, and became part of a political structure that could mobilize resources to address famines, conflicts, and natural disasters. The stones they moved were not just building materials. They were statements of capability, demonstrations that this civilization could accomplish what seemed impossible. When subject peoples saw the walls of Sacsayhuaman or the terraces of Machu Picchu, they saw proof that the Inca could reshape landscapes and bend nature to human will. That psychological impact may have been worth more than any military victory. The Spanish eventually conquered the Inca Empire, but they never matched its engineering achievements. The buildings they constructed on Inca foundations crumbled during earthquakes. The roads they built required constant maintenance that the colonial government couldn't sustain. 5 centuries later, Inca stonework remains, silent testimony to a civilization that solved the problem of moving 100-ton stones without wheels and built an empire that reshaped a continent. The answer to how they did it lies not in any single technique or tool, but in a comprehensive approach to engineering, organization, and society that modern civilization is still learning to understand.